Okay, let's get underway. Apologies for the delayed start to today's proceedings. That was all my fault, so apologies for that. But today we're underway with our 7th of our DARA e-seminars, and thanks again, many of you for joining. It's a real pleasure today to welcome Professor Roger Deane from the University of Pretoria. So Roger is, I'm sure, aware to many of you. He's been a big friend of the DARA project over the years, and today he's going to tell us about the exciting discoveries with the EHT. So this is another sort of global interferometer project, but this time operating at millimeter wavelengths rather than down at the centimeter wavelengths like the AVN and eventually SK will do. So Roger did his PhD at the University of Oxford with our late friend Professor Steve Rawlings, who was a real inspiration to many of us and kind of got me thinking about collaborating with Africa way back many years ago, and sort of probably is partly responsible for leading us to where we are with DARA at the moment. So we have that shared heritage. After his PhD in Oxford, then he's had several postdoc positions in South Africa, Cape Town, Rhodes, and now Pretoria, where he's on the faculty. And so without further ado, I will hand over to Roger to get us underway. As usual, please type any questions you think during the talk into the Q&A box, not into the chat box. You don't need to register or anything. That's all been captured already. So just put your questions in the Q&A and we'll deal with those at the end. Okay, so over to you, Roger.
Great, thank you very much, Melvin, and thanks, Patricia, for the invitation. I'm really delighted to share with the DARA current cohorts and some past cohorts. Members of past cohorts. I can see a project that I've been just so excited about and delighted to be a part of. Yeah, you mentioned Steve Rawlings and how he played some part in you getting involved in DARA. I think what you and Patricia have done with DARA is, I think you'd be absolutely delighted. But we can chat about that at some other point. I'm sorry that I'm not talking to you in live in Hartra, as has been the case in previous years. We obviously find ourselves in an unprecedented pandemic, but I am very glad that we can reach out to you in this format. And as I say, today I want to talk about, and Melvin mentioned, interferometry, but what some people call extreme interferometry. And it's still radio astronomy. It's at the millimeter wavelength. I'm going to have to steal the screen. Can I do that?
Yeah, go ahead.
Yeah. All right. It's still radio astronomy, and it's this global array, which you can see at the bottom left here. Can everyone see the entirety of my screen? Where is the nice? I don't want an annotate. I want a laser. Sorry, begging your pardon, but for some reason I've lost control.
We could see your cursor, okay, Roger?
You can. Okay, cool.
Yeah, and the whole screen as well.
All right. Let's hope that we don't have to go back. But radio interferometry, but on mountaintops, and I'll get to why in a bit. But much like the African VLBI network is envisioned and the full extent of the square kilometer array mid-frequency component, dishes spread across thousands of kilometers, up to 10,000 kilometers in this case, but just operating at slightly shorter wavelengths, higher frequencies. To try and image something called the black hole shadow, which I'll explain in a bit, but you see a simulation of that on the front on this cover slide. I really need to emphasize that this is a a talk given on behalf of a large collaboration, many people that worked tirelessly over many decades, in some cases, to get to where the EHT is today. I'm very much a latecomer in the collaboration and just delighted to be a part of it. But here is a photograph of us at our collaboration meeting in Nijmegen in the Netherlands back in November 2018. This is 6 months approximately before we announced our first results, and you can see everyone's got a bit of a Cheshire cat smile on their faces, because at that point we had a big secret that we couldn't tell anyone. But these people are across the board. Radio interferometry, specifically VLBI, requires collaboration across many countries across the world. So in your get to know your colleagues across many countries well, because you'll need to collaborate with them strongly as we look forward to the African VLBI network and the Square Kilometre Array in the future. And yeah, the EHT is definitely an example of this. It's, of course, I have to mention the stakeholder institutes, which put a lot of the money ahead and make the facilities available to do these fantastic observations. So these are the 13 stakeholder institutes. And these are the affiliated institutes. And you can see there, University of Pretoria and Rhodes University are members. I hope to see more African institutes become a part of the EHT in the future, but I'll close with a discussion on that in this talk. So the subject of this talk is basically this image, what some call a fuzzy donut, but I'm sure quite a few of you saw this image of a black hole shadow, that central depression and the southern brightening. I'll describe what that is in a moment after describing what a black hole is. But it's been rather bizarre. I mean, we work hard on astronomy and we kind of have our heads buried in code. But it was bizarre that looking up, suddenly this was kind of, took the world by storm. It won the Breakthrough Prize, which is the so-called Oscars of Science. You can see Mark Zuckerberg there presenting a previous Breakthrough Prize. You can see our founding director of the Event Horizon Telescope, Shep Dolman, meters away from Lenny Kravitz, which is just a bit strange, trying to make sense of how astronomy can have such an impact. But it's something to remember. And this image was on the front page of many newspapers, which also just kind of completely blew us away. You can just see that in many countries. And just a reminder how astronomy can really capture the public's imagination. It also does wonderful things like set the internet alight, and yeah, really enjoyed all the memes. Perhaps these are the more important publications of that day, but some wonderful and some not so politically correct internet memes that were remarkable. I think maybe the favorite or least favorite is for Melvin is what Brexit looks like from space, but we'll leave that conversation for another day. For South Africans, it's definitely the ESCOM comment, but yeah, I won't go into the details of that. But it's estimated that at least 1 billion people saw this image, and I think it's extraordinary the reach that astronomy can have. Yeah, it's important to kind of stand up and look around that. But I want to move a little bit past the headlights today and dive into this image and tell you a little bit more about what actually went into that, and beyond just this the why of imagination, but actually into a little bit of the details, which links up with a lot of what you're learning, what you will be learning about, and those that have come through in previous cohorts, what they've learned about. So the first question that many of you might have is, well, how can you see if it's a picture of a black hole, how can you see an image of something that by definition, light cannot escape from it? And the answer to that is, well, you're not seeing the things come out of the black hole. You're seeing very energetic phenomena in the immediate vicinity of the black hole. So here you see an accretion disk with hot plasma swirling into the black hole. And then through twisted magnetic field lines, we believe jets being launched towards the top and bottom of this. And really, we are imaging the black hole in silhouette, we're seeing this hot plasma and then a depression towards the black hole, or decrement of light towards the black hole, and a bit of a sharp feature on that in that vicinity. Before I go into more detail on what an actual shadow is, I just want to talk a little bit about the size of black holes. And this is one of the incredible things, and for those of you who might go on to study active galactic nuclei and supermassive black holes, is just how the prevailing theory of how they can actually influence their surroundings in a remarkable way, despite being what you will see is absolutely tiny. So the size is the distance at which light cannot escape. You would have heard that before. It's known as this event horizon. That's hence the event horizon telescope. And it depends only on the mass and the spin of the black hole. A black hole can have charge as well, but in most astrophysical cases, it seems that that would be dissipated very, very quickly. So a nice way to think, for me at least, about the size of a black hole is it's this distance at which light cannot escape. So if you think of this waterfall, this is the Niagara Falls on the border of the US and Canada. And you can imagine how the water flows faster and faster towards the edge of the waterfall. And you can imagine yourself swimming in the opposite direction very vigorously. There is some distance away from the lip of the waterfall, which if you're swimming at your maximum distance, at maximum speed, you would not be moving. You would just be staying in position, which would be very scary indeed. And in an analogous way, space-time is almost sort of falling into a black hole, and the distance at which light has to travel to stay constant, just escape, is that size of the black hole. I don't know why I went back a slide there. And it's a really simple equation that actually describes that radius in the non-spinning black hole case. This is a so-called Schwarzschild solution and the Schwarzschild radius of the black hole. And there aren't many equations in this whole presentation, I promise, but here R is just that radius, so that red line, the size of the black hole, and it's twice Newton's gravitational constant times the mass of the black hole, how much mass is inside that black hole, divided by the speed of light squared. And we all know the speed of light is a very large number, so if you divide by that squared, well, you're going to make something that's really small. And black holes are indeed exceedingly small. So that's the size of the event horizon. So what then is the shadow? What do people mean by the shadow? And to explain that to you, and hence what this actual orange image is, I need to explain two concepts. So the one is that you've got light bending happening around the black hole, and then you've actually got light captured by the black hole. And this animation kind of describes those two things. You see photons that are that travel near the black hole actually get curved or bent by the black hole, distorted by because of the local space-time distortion. And some of them actually get captured. And if you look at that from a different angle, you would see a brightening because longer path lengths in the immediate vicinity of the black hole. But then you would also see this depression or deficit of light where the photons are actually captured. And that was the signature that was predicted in simulations for years and years. And that is what we believe we're seeing in this image that was released in April of last year. So seen in another way, here's another animation where you've got plasma in the immediate vicinity of the black hole. Now we're seeing it sort of edge on. Some of those photons are being captured. Some of them are being bent completely around the black hole. And the net result, the observational signature, is this black hole that's backlit by this bath of photons in its immediate vicinity. And that was the objective. But remember, divide by the speed of light squared. So this is a really, really small, and hence the reason we need to use VLBI. So going back to that animation on the left there, you can see the accretion disk and the jets. And what you'll do in centimeter VLBI, those that study AGN or young stellar objects, looking at jets, you'll see these outflows, relativistic jets, whereas the shadow is right in the innermost part here, close to the event horizon. And what you'll see is that there's that event horizon, the size of the black hole, which would be the Schwarzschild radius in the non-spinning case. And then there's this photon ring that is further out because of this light bending, gravitational lensing, for those that might have read about that. And if you look with different instruments, so with ALMA, for example, you would see these jet-like features. But with EHT, we're diving in right in the center here and looking for that silhouette-like feature. Okay, so, well, how do you go and make an image of this feature? You've predicted that it may exist. There's very hot plasma in the immediate vicinity. There may be jets. How do you go about that? And I'd like to talk just a little bit about the imaging process, because later on in Unit 2 and 3, and then in more detail in Unit 4, you'll dive into that, and those that have already gone through the DARA program will know this quite well. The EHT and the AVN and the square kilometer array and Meerkat are not digital cameras. One does not merely simply point and shoot the EHT and get a photograph that you pop on the cover of the New York Times. No, not at all. And the best way to think about, well, the best way, one way I like to think about this is that the EHT is an interferometry, like the AVN, is like a broken mirror. And you've got to stitch it together. And you do that using software, because you can't build a dish that is the size of the Earth, which is what's effectively required. But you can record signals at individual sites, and you can see those sites at the bottom there, and I'll show some more detail on these sites in a moment. And you effectively stitch these individual signals together in the same way that the African VLBI network would do, in the same way that the current European VLBI network, for example, does. Record signals at individual sites at high time precision and accuracy, and then bring them together, stitch them together using software, and synthesize a virtual telescope. So this is a slide I use in my third-year course. That is a building at the University of Pretoria with some nice periodic structure. You can see the different floors, so the horizontal lines. Then you can see the different windows, the horizontal lines, and the vertical lines on the windows, the dividers between the windows. And then there's a big white thing in the middle and two dark things on either side of the building, the sky. And what you get with what's called a 2D Fourier transform, you'll learn more about interferometry later on. Those that have will know what I'm talking about. But think of it as an abstract mathematical representation of all the information that's contained in that image of that building. You can see some structure, it's mostly noise, but there is some clear structure. And what our virtual telescope does, because we don't have dishes covering the entire Earth or all of Africa in the future, I beg your pardon, we sample a small part of that, which you can see on the bottom right. Just a little bit of information. And then we use that partial bit of information to try and reconstruct what is in reality there. So you can see the image on the bottom left is not a perfect representation by any means of that building taken with a digital camera. But you are getting a lot of the key features. You can even see hints of people in the front. I mean, not fantastically, but you can certainly see the different floor levels. And so where you sample tells you, determines what features you can extract. And then where you put your antennas determines where you sample these key components. So the EHT does the sampling, and it uses the extremity of the Earth as well as the extremes of the Earth. And what I mean by that is we effectively have to build a telescope, separate antennas as far as possible, because as you'll learn, you've got to have as far a separation as possible to get higher angular resolution. And at the observing wavelength we are at 1.3 millimeters, which is a bit higher than the African VLBI network, what it all operates at. You basically have to have 10,000 kilometer baselines in order to see that tiny, tiny signature of the photon ring around a supermassive black hole. And so we have to put these antennas far apart, but it doesn't just help to put them far apart. They actually have to be as close to space as possible. We can't really put them in space, not effectively, because they're all really, really heavy. And they're really heavy because, as you can see, they're quite chunky on the right-hand side there. And that's because the wavelength of light is 1 millimeter. And as you'll learn later on, your dish surface accuracy has to be at least about a 20th of that in order to robustly capture the light and focus it without losing too much of the efficiency. So these need to be chunky, they need to be far apart, and then they need to be in what you can see are fairly extreme environments. You can see a volcano in the background of the Alma dish in the middle right an image. That's Alma, the sort of SKA of the millimeter world in Chile. On the bottom right, you can see the South Pole telescope. That's at the South Pole. It's a fantastic place to build telescopes. And the South Pole telescope, which was originally designed to look for the Sunyaev-Zeldovich effect, inverse Compton scattering through galaxy clusters, participates in the EHT and plays a critical part because of its strategic geographic location. On the far right, interestingly, just on the side, you can see the BICEP experiment, which is looking for primordial gravitational waves from that are signatures of inflation. But anyway, so the extremities of the Earth and the extremes is what's required to operate the EHT. It's very few antennas, as you would have seen before, and the reason the SKA is a big data problem is because it's many, many dishes, and you need to combine them all. You put all the expense in computing. But the data problem with the EHT is not to be sniffed at either, even though they're just a few sites. Excuse the airplane that's going right now. So the data is recorded at these different sites. And in fact, I just mentioned the South Pole. The observations happen in April, and we only get these disks 6 months later because one can't move anything out of the South Pole or the Antarctic region during winter. So that's just one of the reasons why I think people call it this a bit of extreme interferometry. Anyway, so these disks have these very recorded data at high time resolution and frequency resolution, which is then shipped to MIT and the Max Planck Institute for Radio Astronomy in Bonn, and it's correlated. You'll learn about correlation, which is this combination of the signals from individual elements of an interferometer in order to form what are known as the Fourier components. Many of you will learn about that later on. And in total, that's about 4 petabytes of data that are recorded from 8 different stations. Now, it's because it has to be recorded at such high time and frequency resolution, but nonetheless, that gives you a hint of if you start scaling that up to larger arrays with many more elements. And in fact, the EHT is going to have a big problem at the moment in the near future with increasing bandwidth and more stations coming online. The data rates will really increase dramatically. But what's interesting is we go from about 4 petabytes to a final image size. You saw it. You saw the pixelated image right in the beginning, right? It's a few kilobytes. And it's something that sort of boggles my mind a bit. We spend a lot of time reducing a lot of data, and what we get out is this tiny little image. But I think it's important not to get discouraged by that kind of thing, because the payoff is big when you make a nice discovery, and I'm sure you will all experience that in the near future. So in summary, it's this global array of antennas, or these shards of broken glass that you can see on the left, and the Earth rotates. This is seen from the center of our galaxy, Sagittarius A star, the 4 million solar mass black hole at the center of our galaxy. All those points that you're seeing on the left there, connecting the different baselines, are at extreme locations on top of volcanoes or South Pole, but generally at sort of 5,000 meters or just in very, very high and dry sites. And we're trying to image this, this plasma that is orbiting around the black hole, a little bit beyond the event horizon, being distorted around it, bent with longer photon lengths, and therefore edge brightening around the black hole, and then this depression or decrement of light right in the center where the photon capture happens. And just to put it in perspective, that signature in the M87 case was effectively the scale of, putting a donut on the moon, which is about 1,000 times better than what the resolution that we've imaged the moon at from Earth. So that was the image, and to put that into, everyone loves XKCD. If you can put our solar system right in the center of that black hole. M87 is this enormous black hole, and I'll return to the source itself in a bit. But what you see in the press, I mean, the New York Times only showed one image. One of the cool things about this experiment is there are many images. So April 11th, 2017 data was probably our best image. But you can see there are several images that are fairly consistent with that. And we had different weather conditions. We had different scan, different number of antennas that were participating at different times, so different UV coverage for those of you for whom that makes sense. And so the experiment was repeated just over the course of 4 days. But on top of that, we didn't make just one image. Those who've wrestled with deconvolution and how deep to clean using the clean algorithm, we used 3 imaging algorithms. So the one on the left there is DiffMap. That's a clean type of algorithm for those that are familiar with clean. DiffMap is an algorithm that's been used in the VLBI community for about 40 years. And in contrast, the 2 algorithms in the middle and on the right, EHD imaging and Smiley, use a completely different approach. They use what's known as a forward modeling approach, using maximum likelihood methods in order to capture, image in a very different way. But what was really encouraging was get very, very similar structure. So that gave a lot of confidence to the results. What's really interesting then is to compare with, I showed you what we expect from simulations, and now, a huge effort went into comparing with what, with the observations, what was actually expected. So what you can see here are three snapshots of 3 different simulations. These are called general relativistic magnetohydrodynamical simulations, looking at the plasma and its emission in the vicinity of the black hole, but also folding in the distortion due to the local space-time and the bending and the distortion of light paths in that vicinity. And what you're seeing there, you can see some strange thing called SANE and MAD. Those are the different magnetic field models for what we think are viable models for what's going on in the vicinity of the black hole. You can see the A star parameter, that's actually that spin of the black hole. So 0.94 is almost maximally spinning, the plasma is spinning with the black hole in the same direction. A star equals 0 in the middle there is a stationary black hole, so a short-trailed black hole. And then on the left, you have counter-rotating plasma to the spin of the black hole. And then the R high parameter is just a parameter that captures the electron-ion temperature ratios. So there are a few parameters that go into this, but by and large, if you then push that through an interferometric simulator, which is what we built as part of the EHD collaboration, you see a blurred version of that. And that's what you see in the bottom row there. And what you're seeing there is qualitatively very, very similar to the fuzzy donut I showed you right in the beginning, which is the observational model. Those are all simulated black holes that seem to match very close to what we observed. These are not best fits. They are simply just representative of the library of models that are tuned to M87. So let me tell you a little bit about M87. Here's this beautiful optical image of the galaxy. It's this elliptical galaxy. For those that have dealt with a bit of introductory astronomy, you'll know this is an old, very massive galaxy. It's mostly devoid of gas and dust. Star formation has mostly ceased. It's got a really massive black hole as a result of being very massive. It's very nearby, 55 million light years away from Earth. It is pretty nearby. It doesn't seem like it. And I love this animation. I can kind of stare at this for hours. It's a cosmic tennis match of a photon traveling between the Earth and the Moon. Now imagine that for 55 million million years. That's how long the photons that traveled from the M87 black hole took to reach our telescopes. But nonetheless, it's still pretty nearby. Let's turn off that before our next go into a spasm. But if you look at M87 through radio eyes, and if you look at it at much lower resolution than what the EHT provides, so with a very large telescope that's based in Socorro, New Mexico, you can see this amazing jet-like feature that travels out to the top right, and you can see this lobe of emission in the immediate vicinity. For those that have learned about it, there's this Doppler boosting effect where you see Doppler brightening of the jet coming towards you. That's why it looks kind of one-sided in the inner part. And then there's a bright core of emission right in the center. And we dove right in the center there, the EHT at 230 gigahertz to get that maximal angular resolution. And actually the source becomes opaque at higher less opaque at higher frequencies, which we required to dive through that plasma. And we were able to capture that image. So that places, radio astronomy covers many, many different energy scales and many, many, many different spatial scales. And you put yourself in a very strong position to understand sources when you combine those two. And certainly the study of M87 has required this. A master student of mine has got, is studying M87 closer to the VLA at 1.5 gigahertz right at the top there. Light, but using meerkats and seeing some very interesting things so far. Anyway, so that's great. We're imaging the shadow of a black hole. So why? One of the chief reasons is because the morphology and the size and the shape of this black hole basically encode what the rules of gravity are. How gravity works. Now, our leading theory, as most of you will know, is general relativity has passed pretty much every test that's been thrown at it in the last 105 years. So it's, but one needs to do higher and higher precision tests, and also to do so in different regimes. And the immediate vicinity of a supermassive black hole is not a regime that's been tested as tightly as with these observations with the Event Horizon Telescope. Now, it's important to remember that shadow feature changes depending on your inclination angle and depending on the spin, and then obviously the mass scales the size of it. So this is a nice animation from Jeremy Schnittman from Maryland, JPL, and he's showing the inclination angle of that thin plasma disk changing. And you can see how the shadow feature in the center changes as a result. Also, another problem we have is that even if you keep that inclination angle constant, the immediate vicinity of a supermassive black hole is highly dynamic. Material is moving at very, very high velocity. And so the image is changing, which violates one of the fundamental assumptions of radio interferometry, that the sky is static. And that complicates a lot of our analysis. Just to by the by, another master student of mine, Michaela Menegaldo, is taking in this huge library we have of black hole shadows that are simulated in supercomputers. And she's using a self-organizing map to organize them and see if we can classify them in a self-learning type manner. So she's tested this with one particular simulation library, and you can see here that the algorithm has self-organized these into different cells, and you can see some of these shadows are more puffy than others. Obviously, the sizes are automatically sorted, but that's a bit of work that we're doing at the moment. Okay, so I want to close out the last section of the talk, talking about what's next, and then linking up to the possibilities for the African continent. So one of the key things we want to do is, of course, I emphasized that it wasn't just one image. We took multiple images of the time scale of a week, effectively, back in 2017. We want to repeat the experiment on year-long timescales, because basically the time that it takes for plasma to orbit around M87 is of order months. So to really see significant changes, you want to be re-imaging that on longer timescales than just a few days. I didn't really mention it previously, but there is a hint of differences in those images and some dynamical evolution, but we chose to not really explore that in the first publications. Now, what's interesting is that one of our next targets is, one of our two primary targets is Sagittarius A star, the black hole at the center of our galaxy, which is 4 million suns of mass. And that black hole, the orbital timescale is about 1,000 times shorter, which means that things can orbit around there on the timescale of minutes rather than months. And the idea there is that we're just going to try and make a movie of that black hole, the plasma that's moving around. Yeah. Sorry, there seems to be a barrage of aircraft this evening. So the movie of the black hole is one of the key next objectives. Then a big focus at the moment is polarimetry. Some of you may have done, those that have passed through DARA in past years, may have done polarimetry tutorials with CASA. Basically, we're trying to look at if there are any preferred light orientations towards that plasma, because that tells us a lot about the magnetic field structure in the immediate vicinity of supermassive black holes, which is critical to understand how they actually feed themselves and how they grow, as well as the jet launching mechanism. These are very, very key aspects of that. And then a big focus of the EHT is to actually expand the array, put more shards of glass on the Earth, and in order to make far sharper images, and really get to that one of the primary targets, objectives, which is to really start robustly testing gravity theories, different theories of gravity. Okay, so the case for expanding the EHT in Africa is pretty clear. These are the existing stations from 2018. There are a few that are being added in Europe and North America. But you can see that Africa, this is from celestial equators perspective. You can see that there's a lot of space there to put shards of glass in Africa. But if you had to shift this orientation to Sagittarius A star, which is at minus 29 degrees, the missing elements in Africa become even more apparent. And I'll show an animation that shows, that demonstrates that in a moment. Here's a little animation that shows just the value of adding more stations. So here you see a single baseline, then you add an extra few telescopes. You start to see the UV coverage, for those that understand that concept so far, build up. And on the right, middle right, we're seeing the flux density as a function of UV distance or baseline length, longer baselines to the right. And as you add more and more samples, you improve your ability to image that plasma that is in the immediate vicinity of the supermassive black hole and actually make out that silhouette type feature. So we want to continue that. This is the UV coverage from the 2017 observations. We want to fill that UV plane as any radio interferometry observatory wants to do. And we want to improve our imaging quality significantly. So one project that's going after this is the African Millimeter Telescope. This is a partnership between Radboud University and the University of Namibia. So some of the people on this webinar may know about this quite well. And essentially, the objective is to put a 15-meter dish on a very, very flat top mountain at 2,300 meters in Namibia. I think it's the third highest mountain in Namibia. Extremely dry, a really good site, and really well located globally to contribute to imaging the Sagittarius A star in particular. This is me standing on top of that mountain. I was really lucky to visit Namibia last year, and yeah, I'm looking nervous because I'm right on the edge of that road there, and I just traveled this journey here, which was one of the more scary of my entire life. But there are considerations to look at other sites around Africa, and I think the value would be incredible for Sagittarius A star, that faster black hole, if I may call it that, because it's lower mass and therefore variable on much shorter timescales. There's the dish that the AMT team envisions will be on top of the Gamsberg mountain. It's the Swedish ESA submillimeter telescope assessed, owned by ESO and Onsla Observatory, and there's a lot of work going on to try and get that dish there. But more broadly, that's one particular project that's very relevant to Africa, but more broadly, EHT is looking at expanding across the world. There are multiple sites proposed. So you can see that in yellow were the sites from the 2017 run. You can see in orange, these will be new sites. They would have been available for next year's run, but it's looking like because of COVID, we won't be able to do next year's run. And then in this turquoisey color is proposed sites. And you can see the Gamsberg is one of those. There are a few in South America and a few across North America. And this would really improve our imaging quality significantly to do this. And here's a simulation basically showing a bit of that on the far left. You can see a simulated image of a black hole shadow. Remember, there is always a jet. It's just that with EHT, we kind of filter that out. You can think of an interferometer as a spatial filter, and we filter out a lot of that larger scale emission. You can see the EHT 2017 ability to image that. And then you can see how dramatically that improves with the NG EHT from the previous slide that I showed. Those additional sites allow you to make a far sharper image of the shadow of the black hole, and therefore make far more robust and better constrained comparisons with what different theories of gravity predict that shadow should look like. Polarimetry will be a major, expanding the EHT will be a major boost to polarimetry as well. And you can see here an example of just how well the polarization vectors could be recovered with the NGHT from a simulation that is blurred to EHT resolution, doing very well in recovering that magnetic field structure, which is so critical in understanding accretion and jet launch. Here, this gets really interesting, actually trying to recover the orbit of individual plasma hotspots in the immediate vicinity of the black hole, especially for Sagittarius A star, where the timescales here are of order minutes. And you can see on the top row with the EHT 2017, you can see it's fairly blurry and you can't see huge evidence for a hotspot there. But as you move to the NG-EHT, and you can see that ground truth image, a lot of that detail is recovered. More ambitiously, there are plans to try and go to space. This is a study led by Frederick Rilof's PhD student from Radboud University. There's some work going on in the US looking at various spacecraft concepts for the EHT going into space. But the idea here is quite interesting. You're seeing, for those that are familiar with UV coverage, here the idea is to put 2 spacecraft and potentially 3 in orbit, and you put them on differential orbits, which I'll show in the animation in a moment. And because they are on differential orbits, they have different separations, which evolve over time quite rapidly over the orbit. And you can design it such that you have nice spirals across the UV plane and get really, really high quality interferometric imaging. You can see the image on the right there. That is not typical of the kind of noise and correlated noise that one expects in an interferometric image. It looks a lot more pixelated, and that's because of the fact that the UV coverage is so good. So they're the 2 spacecraft on different orbits. They go to different separations, and they trace out this spiral pattern in the UV plane. So going to space VLBI really is a huge potential. So here's another simulation on the top row there. You're seeing different snapshots of that, different times. EHT 2020, what that would be able to recover. M there, the units of time are encoded in units of mass of the black hole, because remember the orbital timescale scales with the mass of the black hole. So you see EHT 2020 is recovering some structure, but if you had to include a satellite in low Earth orbit, so a few hundred kilometers above the Earth, of order about 300, you can recover a lot more detail, a lot more sharper features, because you get those longer baselines. And this will be interesting not only for making better images, but what I'm showing on the right there is that our 2 primary targets are M87 and Sagittarius A star. That's because they're the right combination of near and their mass means that they're the largest apparent shadow diameters on the sky. But there are other black holes that, if you just improve your resolution a little bit, come into play and make EHT far more of an observatory than just an experiment mode telescope with, you know, 2 primary targets. So yeah, expanding the array in this way, huge potential. I won't chat about that. I just want to close out 1 or 2 more slides because I see I'm getting close to time. Many of you will remember this, this beautiful image released by Meerkat of the center of our galaxy from 2 years ago now. Right in the heart of that lies Sagittarius A star, and this is a simulation of the plasma orbiting. So if we get really ambitious about multiple stations on the African continent, which you'll see as the Earth rotates on the bottom right there in a moment, then we really get superb imaging quality of the orbiting black hole in the center of our galaxy. And what you can see, look at the timescales on the bottom right there. This is on the timescale of minutes, just beautiful imaging. And this really becomes a gravity experiment, a gravity machine, if you will. And yeah, this is a wonderful simulation by Michael Johnson from Harvard. So a summary slide. I hope I've demonstrated, I haven't spoken so much about it, but just the engineering excellence that comes behind enabling these huge science results that have come from the EHD. It can't be emphasized enough, and it would be required from the African VLBI network as well as the SKA. We need brilliant engineers as well as we need the brilliant scientists. So I think always keep that in mind. The EHD is it's achieved its primary goal. It's this first image, but really it's just in many ways kind of just getting it really started. There's so much more to come. And I explained some of those concepts, some of those goals to you. It's tough to really make firm or rule out certain theories of gravity at this point with the current imaging quality. Everything's consistent with general relativity, but we really need to expand the array in order to make more firm statements. As I said, it's kind of an experiment mode for now. The primary goal is shadow imaging, but there is a whole range of what we call non-horizon science, lots of other targets that we look at this unprecedented resolution. And then one of the other things, I mean, the astute of you might have noticed that I was talking about the 2017 observations in April, and we released the results on the 10th of April, 2019, and you might have asked yourself, well, it's a few kilobyte image. Why did you take so long to release the results? And the answer is a lot of the tools and techniques that really had to be developed from scratch or close to scratch in order to make this. But the nice thing about that is the impact is much broader than just for this experiment. As often is the case, you have flagship experiments, and then there is software and there are tools and techniques that are developed that have much broader use. And I think I'm certainly within my research group already using some of these within centimeter VLBI. So you'll see some EHD algorithms, no doubt, and calibration pipelines used in the African VLBI network context, I'm sure of it. And then I spoke quite a bit about the EHD expansion, including Africa and space VLBI, which will really significantly enhance our ability to do this. All right, I think I'll close with that and take questions. Thanks very much.
Thanks very much, Roger, for taking us through that story behind that amazing image, and especially the promise of what's more to come. That's really exciting stuff. Okay, we haven't got too many questions yet, so if people have got questions, please type away into the Q&A if you want to ask Roger anything. Again, we can broaden the topics out as well, whatever you want to ask. Be fine. So we've got one in there at the moment, which is from Solomon from Ghana. So let me just allow Solomon to talk, and you can ask your question, Solomon, whenever you're ready. Solomon, can you hear me?
Yeah, can you hear me?
Oh, yeah.
Yeah, I can hear you.
Okay, so thanks for your presentation. All right. So I have a two-part question. So the first one is so I read the research paper published on the EHT results. In there it talks about how we can actually use these radio observations, or these various radio observations will present a new tool for us to explore gravity. So I just wanted to know how this can be done, if you could talk about it briefly. And then the next one is so there's a little bit about how black holes actually form. So we know black holes are actually formed as part of the evolutionary process which galaxies actually undergo. So that's merging and then colliding. So I wanted to know if there were parts of the EHT observation which actually provides information on how galaxies actually form, and also some of these black holes too.
Great, thanks very much for your great question, Solomon. So for the first question, basically different theories of gravity predict different shadow sizes and shapes, and stability, in fact, as well. So in all by their name, I showed you GRMHD simulations of black holes, general relativistic. And that meant that the light was deviated in such a way that was consistent with, governed by general relativity. But you could just insert a different theory which predicts a different distortion to the space-time, and then the light path would travel in a different way, and there would be a different shadow. So here are three simulations. They all assume general relativity, but they have different spins and different magnetic field properties, so astrophysical properties. But if you imagine having a different plane where you didn't assume that this was general relativity and the ray tracing was done conforming to some alternative theory of gravity, the size and the shape of the shadow would be, in many of them, very different, well, quite different. And so by capturing the images, we can then compare with what the predictions are from these suite of different theories, and those which are most consistent with our data would be favored. And that's the way we hope to go about it as we sharpen the imaging quality of the EHT in the future. As to your question on the evolution, that's a very interesting one as well. So I mentioned that the black hole shadow depends on the mass and the spin of the black hole. So it turns out that the spin actually only affects the shadow diameter by about 10%, going from maximally spinning in the same direction to maximally spinning in the opposite direction as the accretion flow. So spin doesn't really affect it enormously, but you would still be able to actually probe that. And spin is actually a way, we think, of probing the recent history of the supermassive black hole. So the black holes that have recently merged may be more disrupted in their spin, whereas a black hole that's been accreting for some time may spin up. And so the shadow size can give us a sense of what spin is of the black hole. And the size of M87, if we assume our mass estimate is correct from stellar orbits in the vicinity of M87, basically the size the size of the black hole is consistent with a black hole that is spinning with its accretion flow and spinning quite fast. We don't have very strong constraints on that at the moment with the current imaging quality, but that is, so that points at a black hole that hasn't really had recent major mergers, but it's actually been accreting for quite some time. And that's consistent with the X-ray and radioluminosity of the large scale jet. So I hope those two answers give you a reasonable idea.
Yeah, it does. Yeah, thank you.
Thanks, Solomon. Next up, we have Nchimi from Zambia. Nchimi, do you want to ask your question?
Hello, can you hear me?
Yep.
Okay, so I was just trying to find out exactly what the motivation is for putting the telescopes right on top. One would have imagined, for example, like the one in Hatra, which is almost surrounded by mountains to avoid radio interference. So what's the trade-off there?
Thanks for asking that question. I realize now that I didn't actually explicitly mention that. So basically, the reason I said that we want these as close as possible to space is because we want as little water vapor between the black hole and us and our telescopes as possible. And so the air gets drier and thins out as you go higher and higher. So mountaintops are generally extremely dry places, and the scale height of the atmosphere is awarded 2 kilometers. So you want to go to high sites to get above the atmosphere, in analogous reasons to why planes try and get above the sky and why we build optical telescopes above. But in that case, it's just general atmosphere. So that can cause a number of effects that are really adverse to the imaging quality of the telescope. So number one is the water vapor actually it simply absorbs the incoming radiation at millimeter wavelengths of this short wavelength. So you lose a lot of your signal, which is bad. The other thing is that you've got Kolmogorov turbulence in the atmosphere. So there is actual scattering of the incoming light. So we can time as accurately as we wish and know exact positions and use atomic clocks at all the different sites. But if the water vapor is scattering out the light, that will affect the phase that we record, and it'd be difficult to get really robust imaging quality as a result. So again, higher gets you above a lot of the more turbulent material. And then also the water vapor, the millimeter telescope actually sees the water vapor, it shines, right? Radiative transfer. So it actually sees emission, and that raises the overall system temperature of the entire thing. So the presence of water vapor actually lessens the sensitivity of our observations in that way as well. So yeah, there are multiple effects, and ideally you just have these in a vacuum or in space, but they're really heavy and expensive to get up there.
Okay, thanks, Nchimi. I think to keep the sort of telescope theme going, then maybe Alex could ask his question next, and then I'll come to Kelvin and Emmanuel after that. Alex, you can unmute yourself and ask your question. You should be able to.
Can you hear me now?
Yep.
Okay, yeah. Yeah, Roger, I wanted to ask, I think from the talk, I do understand that the type of telescopes that are existing are not suitable for such an experiment. So I wanted to know if you could throw more light on that.
Sure. So for the previous link to the previous answer, I mean, they're different because they're observing at these very short wavelengths. And if you want to focus the light, you need the surface accuracy of your dish to be, the rule of thumb is about a 20th of the wavelength that you're observing. So if we take Hatra or one of the other, what is African VLBI network dishes, so in Ghana, for example, Katunzi, if we want to observe at 20 centimeters, 1.4 gigahertz, the dish surface accuracy needs to be better than about a centimeter, 20 times.
Okay.
So if we're observing at 1.3 millimeters, which we're doing, you're looking at sort of 50 micron, which is very difficult to achieve from an engineering perspective, and very difficult to keep at that level. When these things are sitting outside on top of mountains, very remote locations, with temperature swings, and so they have to be pretty hefty. Remember I mentioned that they're quite chunky. These are hundreds of tons rather than you know, a meerkat dish, for example, which only operates up to, well, it's good to about 20 gigahertz with its surface accuracy. It's a lot lighter than that. So those are the two key differences.
Okay, thanks.
Okay, thanks, Alex. And Kelvin, do you want to let me allow you to ask your question? Go ahead, Kelvin. You should be able to unmute yourself, Kelvin, now. If you've got trouble, I can ask your question for you. Maybe. Okay, let me ask away. So Kevin's asking that the gas around the black hole seemed very uneven, and whether is that a result of the Doppler boosting that you talked about?
I got to mention this, which is a key point. Thank you, Kelvin, for pointing this out. So by uneven, I imagine you mean that the southern end of this image is slightly brighter than the top, the northern part. And that's indeed exactly that. So what we imagine is the case, and the ionized gas further out actually is consistent with this as well, is that the gas is moving towards us at the bottom, and it's moving away from us at the top. And because it's moving at a fair fraction of the speed of light, you have this Doppler boosting effect. And the contrast is about a factor of 3, brighter on the southern end. And it's because of exactly that effect that you see this. Yeah, so we think we're seeing the emission come towards us here, and the jet is being actually launched kind of to the right-hand side of this image, but you don't see it in this image. You might be referring as well to unevenness within the actual image. And that's because the plasma, this is pretty turbulent. There are very strong magnetic field lines in this immediate vicinity. And that can lead to some unevenness that's in the simulated image, which would be tough to pick up with this angular resolution, but nonetheless you can see it there.
Yeah, no, it's interesting. So I'd written down exactly the same question to ask myself in a slightly different way, but because the jet angle, if this is to do with the disk, is this to do with the disk orientation then? Because this brightening in the south is not perpendicular to the jet.
Not exactly, no.
Not exactly. No.
So here's the jet coming out here.
Yeah.
It's, yeah, I mean, we can't make very strong statements, but it's within a 15 degrees, I think. Okay. And then at about 20 parsec spatial resolution with the HST, the ionized gas is rotating in this direction, like that, if you can follow my cursor. So it's a vastly different scale, but that is what we expect. It doesn't say much, it's just circumstantial, broadly consistent, but nothing can be firmly stated.
Right, so it's not just happened to be brighter there at that time. If you go back in a year's time, you expect it to be bright in the south again.
Broadly in the south, but we can't say. The position angle does change quite a bit. So if you look at the position angle here in these 4 different images, it does change a fair bit. And there's been quite a bit of work on figuring out to what level is that degenerate with gaps in the UV coverage. If you look at the visibility modeling paper 6 in the series of results, there is some interesting degeneracy there. So position angle is not something that we're confident with at the sort of 10-degree level, but at the 90-degree level, we're fairly consistent. This can also be deviated by hotspots and local phenomena that aren't necessarily indicative of the global spin. I think I've got an image that might show that. Yeah. Where is this? Yeah, but that it's tough to measure position angle, even with the GRMHD images. Yeah.
Another reason to add more telescopes.
Mm.
Okay. Emmanuel's had a hand raised for a while. I don't know if that means he wants to ask a question or not, but Emmanuel, I've put you on the waves.
Yeah, yes, thanks. Yeah, thanks, Roger, for the nice talk. Perhaps I missed this, but your initial discussions focus on Schwarzschild black hole, which is non-spinning. But a more realistic view of a black hole is the case where it is spinning, like a Kerr black hole. So what are the implications for this on the event horizon observations that you guys made?
Yeah, so that changes the size and the appearance of the black hole quite considerably. So we had to factor that into the modeling. So where's an image here? Here you've got different spins. So this is a Kerr spacetime, and this is a Kerr spacetime. This is a Schwarzschild metric. So here you've got maximally counter-rotating black hole and accretion flow. And here you've got maximally, well, close to maximally rotating accretion flow. So that changes the appearance, but in a very subtle way. If you recall, I said that it's basically 10% size difference when you go from this extreme to this extreme. But then you also see there are a lot more, remember this is rotating all the time. It's a dynamical image, movie. And you're seeing this is a lot more, when it's counter-rotating, a lot more, can I say flary? There are a lot more disturbances and disruptions, whereas in the in the positive co-rotating sense, it's a lot more stable, if you wish. So this absolutely impacts the stationary or averaged images that we make, as well as the dynamical imaging that will be done, and absolutely has to be factored into any kind of modeling and parameter estimation process with the data.
Okay, thanks. And just a last quick one. So is there any chance of maybe upcoming researchers or young graduates getting involved in this EAT program, like maybe joining the collaboration or thing like that?
Yeah, for sure. You should have a look at, there are lots of opportunities that are advertised at those EHT nodes and the affiliated institutes, various positions available, PhD positions around Europe, the US, across in Asia. And then my group as well is involved in the EHT. We're an affiliate. I'm an affiliate member as well as my postdoc. And I've got 2 master students working on this and planning to increase, and I'll be advertising masters and PhD positions in the near future. So definitely have a look and look at the partner countries, the partner institutes. There are a whole range of opportunities. In many ways, the EHT, this is the first result, the first major imaging result. The EHT has been around for a long time, but it's really ramping up now. And we need a lot of smart young people to do a lot of this work and take it forward. My great hope is that, and what I'm working towards is getting more African involvement from an infrastructure, telescope, and software perspective. And I hope with that we will raise even more funds in order to support students in building up an EHT fraternity. I mean, the motivation there is to build some of exactly the skills we want to develop for the African VLBI network, for the SKA, and doing high resolution, high angular resolution science.
All right.
Keep you.
Okay, thanks. Yeah.
I'm sure Emmanuel's more interested if you've got any postdoc positions coming up in a year or two.
I do. Keep your eyes peeled. I will be advertising quite soon.
All right.
Just to clarify. Yeah. Emmanuel's just doing a PhD in Bristol. So.
Yeah.
Right.
Okay.
Cool.
Sigrid, you've had your hand up for a while. Sigrid, do you want to ask a question?
Yes, hi. Thank you very much, Roger. This was a very good presentation. In fact, it's the first time listening to it if you had the first session already. And I'm also very excited and happy to hear that the African millimeter telescope in Namibia is part of the EHT as well. I'm Namibian. And I just wanted to find out, I think Solomon have asked one of the questions that I wanted to ask already, and I wanted to find out more on the spacecraft that's in plan. Are they planning to actually use a spacecraft as a telescope with a built-in telescope of EHT, or are they using it as a relay to the existing EHT telescope that's on the ground?
Yeah, really cool question. So there are a number of different mission concepts there.
Okay.
One is that you just have, I showed you two spacecraft orbiting with differential orbits and moving apart. In that model, you just have those two spacecraft forming visibilities with that single baseline, and in that way building up an image over a timescale of a few days to months. Then there is a concept of actually correlating satellite dishes, spacecraft with a very small antenna, because we've got to launch these things up and it's expensive. And then obviously that's got to downlink the data that it collects, which presents a huge problem, because I showed you the huge disks that are collected, and that's more mass and radiation hardening that needs to happen. But that's another model where you actually correlate these dishes. And in fact, I think I showed a result here of the simulation of the image where you had a spacecraft in low Earth orbit. Sorry, here it is, this bottom row here. Spacecraft in low Earth orbit correlated with the EHT 2020 antennas on the ground. So there are many different models. It's going to come down to cost. These are all just costing exercises.
Surely is.
It's going to come down to cost and sharpening the scientific questions. What do we want out of these observations? And I think that through that, it'll go down to a final decision. But what you can see on the bottom, on the right-hand plot there, is actually putting antenna far beyond LEO into geosynchronous, out to the moon, even out to the Lagrangian, in order to look at these, what we call higher order harmonics of black hole shadow feature, which really dives into testing different theories of gravity, not just looking at, but really diving into the detail. Yeah. So yeah, I'll tell you in 10 years maybe. Hopefully, but these space missions are really hard, and they need a lot of consideration and a lot of detailed design work. We'll see what. I can
imagine.
Okay, thanks very much, Sigrid. Thanks for representing Namibia, because obviously, as it's been highlighted, it's quite a key country in all of this. But that's good that you're on. Okay, I think a second question, also from Solomon. He's asked me to ask it for him. So you've mentioned a few times the influence of a strong magnetic field sort of shaping the plasma and everything in and around the black hole. So he's wondering, how strong are these magnetic fields in and around the black holes?
This is a number I always forget, Solomon, because it's tough to relate to. I always forget this number for him, 87. I'll look it up quick. I'll have to look it up quick. Sorry, it's late in the day, not at the top of my head, but I'm sure we can find the answer really quickly. Sorry.
I guess it's not something you're really constraining yet.
We are, but I tend to think about these things in terms of polarization fraction, rather than an absolute number. Sorry, I don't have it at the top of my head.
But yeah, there'll be one for homework.
Yeah,
Solomon.
right back at you, Solomon.
Solomon can email you the question. Yeah. Great. Okay, I think that's all the questions we've had, and that's been really good roam around all the different topics. I mean, sort of a cheeky perhaps from me. I mean, are the Milky Way black hole results going to be coming out, or do you really have to wait before you've got better sort of snapshot coverage? Or
I can't really comment at this point.
Oh, you can't even comment, right? I realise everything's shrouded in secret. Yeah, I shouldn't even ask the question, should I? Yeah, I mean, I'm aware that everything changes very quickly. So it's, I mean, because these are basically self-cowled images, effectively, right?
Yeah. So built into the, I showed the 3 algorithms. The maximum likelihood methods basically build in self-cal with the forward modeling to model the gains. But the self-cal is, we're basically doing it at the scan level, solution intervals, and it's mostly just amplitude that's being done at the moment.
Yeah. So again, more dishes would help, presumably. Yeah,
we benefit a lot from redundant baselines as well.
Yeah.
2017 observations, two of the geographical sites have a pair of telescopes within a few kilometers of each other, and that really helps with what we call network calibration. But I mean, LOFAR uses this for redundant calibration as well, where you know the baselines are the same, so you should get similar intrinsic phases and amplitudes measured. So even additional stations at the same sites will help, but yeah, improving the resolution, improving the number of stations will really improve the calibration. And that's another reason why, and often under appreciated reason why African stations will help so much, is because ALMA, the SKA of the millimeter world, is also in the southern hemisphere. It's in Chile, and there's a lot of visibility, mutual visibility, and key mutual visibility between African sites and ALMA, being at very similar latitudes. And that really would be remarkably strong, good calibration for any station in Africa because of that great mutual visibility with ALMA, and as a result, the improvement of the longer baselines there in an east-west direction would be good. And that's what our sort of simulations are showing already, when you actually include calibration rather than just taking 2D Fourier transforms of different UV coverage.
Indeed. Great. Okay. Well, thanks very much, Roger. That's been an excellent talk, and it's just an absolutely fascinating topic on just so many different levels. Obviously, you've got the front cutting-edge science, but you've got the the infrastructure and the potential for new infrastructure in Africa, and the communication with the entire world of interested in these kind of images. So that's been really good. So thanks very much for that. Trish, do you have any announcements? Or?
Okay, thank you. Yes, so basically I too would like to thank Roger for giving a very informative talk and for continuing to support DARA. I think you've been part of the team for around 6-7 years now, so thank you for that, and thank you to the participants for asking a great array of questions and challenging the speaker. So thank you for that. Feedback is very important to us. We will continue to host these seminars, so I'll send out the form to everybody, so please kindly complete that as soon as possible. It gives you the opportunity to also put forward suggestions for future seminars. and indeed anything else that you think might be beneficial for DARA to deliver. Future e-seminars, we are in the process of scheduling more. We're now in August, and typically academia tends to come to a little bit of a grinding halt. So please bear with us, and I will announce any future e-seminars via email, on our Twitter account, and also on the Facebook page. Just to confirm, we have recorded this e-seminar, so if you do want to go back and have another watch, it will be made available on YouTube at some time next week. All of our past e-seminars are also available there. And I think that's everything I have to say, so I'll now pass over to Melvin.
Well, I don't think I can add any more, other than just to thank all the audience for turning up once again. And it's good to see and hear people. So many thanks for keeping in touch with the project and keeping up to date with all these developments. Well, as Trish says, we'll be back again with more in sort of September time. So again, thanks to Roger once again, and we'll leave it there for now. Thanks, everybody.
Thanks.
Great. Thanks a lot. Good to see you.
Bye.